us started. If any of you are, any of you out there in the cybersphere are wondering, the Westlake girls basketball team does have pizza cards.
Only buy it from Michelle, though.
Contact Michelle Apple.
Michelle Apple. Yes. Yeah, actually, people do. I actually, over the past it's kind of weird. Over the past week, my YouTube account is linked to my school email, and I've gotten 5 or 6 just random people that commented on old ones that I posted last year. It looks like they're like physics students in college or something, and they're like, I watched your video, it was awesome. And I was like, thanks. So, but yes, people do watch it. So.
I watched one of them, but it was late at night because I didn't understand something. So I watched it and I was falling asleep.
Yeah, I mean, well, if you're watching it late at night, and you're just
actually in class, you're just watching the board.
Yeah, you're just watching the board, so it's kind of yeah. Yeah, I wouldn't recommend watching it late at night unless you are trying to fall asleep. So. Yes, kid.
Wait, you know the one teacher that posts videos on YouTube of him rapping about the subjects?
I've seen that before, but I am not going to do that. So, just so you know.
Can we listen to the Element song?
Yeah.
No, we should listen to Daniel Radcliffe singing.
Can you play one
On the Grand North
class?
Yeah.
All right. Getting back, it's the flame that never dies.
Wait, all of this is on the recording.
Yeah, we're getting all this. So, thank goodness.
Watch this video today, no one will laugh.
All right. Wednesday for you guys, we started in on our next unit, that being the electricity unit. So starting off, we did the discovery lab at the beginning of class, and then we did the guided reading practice afterwards. How you felt about the guided reading practice? Okay, some of you probably liked it, some of you probably didn't think it was all that great, whatever. I'm going to try and give you guys different strategies that you can use to make sure that you are understanding that text material, because it is one of the skills that you need to develop if you're going to be good going forward as far as college and things like that. Okay? I may not always give you that same graphic organizer. Maybe we'll do some other things as the year goes on, but we'll give you some different ways to look at it. Okay? Today, we're going to formally introduce electric charge. We'll fill out the outline. Hopefully we'll get through a good portion of it because a lot of it is similar to what we talked about on Wednesday with the guided reading stuff. Okay? Then, getting into next week, we'll get into the next topic, which is current. I'm anticipating that the outline from today is going to spill over into Monday, so we might do like a short guided reading on Monday, just over like one section of the next part. Then we'll get into current on Tuesday. Your first quiz for this unit will be on Tuesday as well over electric charge. It's an open note quiz, right? Just making sure we're keeping up with the things we're supposed to be keeping up on. Then, next week on Wednesday, you'll do your next lab for this section, and it is a virtual lab, so it'll be done in the library. We're going on to the library the second half of the block. So the first half of the block, we'll introduce some circuit stuff, then we'll take you down to the library, and we build some circuits on the computer. I think it's a pretty cool website. I think it does a good job of explaining how things go and showing you like light bulbs and how bright they are and stuff like that. So we'll see that when we get down there. Then next Friday, we'll do circuits and we'll fill an outline, make sure that you understand all the things that you saw in the lab on Wednesday. That will leave us Monday of the following week to wrap things up and review and test on Tuesday, right before Thanksgiving break. Okay? Good there? Questions? Okay. Let's start with the outline and make sure, like I said, hopefully the beginning part of this, a lot of it sounds familiar because it is a lot of the stuff that we did in the reading on Wednesday, so hopefully we'll get to go through this pretty quickly. Okay? But first, it starts off with this table, and the table is too big, so I'm just going to do this, and, oh, too far. So, anyway, let me do this. Grab this table, and apparently not move it up. There we go. All right, you've seen this table before, yes? Okay. We looked at this table when we were looking at subatomic particles and getting into what's inside of an atom and stuff like that. Why do I bring this table up again now at the beginning of this unit? Joe?
Because it shows the charge of
Okay.
the proton.
So on your outline line, Joe, the first thing that it writes down, right? It says electric charge comes from blank. Where do electric charges come from, Gabe?
The orientation of electrons and protons.
Okay, so more generally, we call electrons and protons what? What was that general name we kind of gave for them? Not atoms, but
Well,
parts of atoms or subatomic particles, right? So electric charges come from subatomic particles. That's what they are. They're pieces of atoms, separate from the atom itself. Okay? So electric charges come from subatomic particles. They're parts of atoms. Good there? All right, let's talk a little bit what comes out of that. Next thing, charge is quantized. Quantized or quantization is a word that we've come across before. Does anybody remember where we introduced the idea of quantization? Mingda. The energy levels in what model of the atom, Mingda? Bohr's model of the atom, right? If we pull up a Bohr model of the atom, right? There's some Bohr models, right? What did we say about where those electrons could exist? In those defined rings, either here or here or here or here, but not anywhere in between. That idea is quantization, that there's a certain amount of energy, because remember those rings relate to energy, right? There's a certain amount of energy that can exist, but it has to exist in defined chunks, okay? What we find out is that charge is quantized as well. There is a minimum amount of charge that we can have. What is that minimum amount of charge? Gib?
0.
Not 0. I suppose that is, you could have 0, but if we're talking about measuring charge, right? What's the minimum amount of charge that we can measure? Where does charge come from? A subatomic particle. So what's the minimum amount of charge that we can measure? Mingda?
-1.
Not -1, but it's the charge of what, Mingda? How many particles? 1. Okay? There's a minimum amount of charge that can exist. It's the charge of 1 electron, because that's where charge comes from. Every other charge that we measure is going to be some integer multiple of the charge of 1 electron. Because you can't have parts of an electron or parts of a proton, right? That's what we say, that's what we mean by saying that charge is quantized. There is a smallest amount of something, and every other amount is some integer multiple of that amount. Another thing that is quantized, money, American money. What's the smallest amount of American money that you can have?
1 cent.
1 cent. Every other amount of money is some integer multiple.
pennies.
What?
Hey, pennies.
Yeah. But anyway, every other amount of money out there is some integer multiple of 1 cent, right? That's how money works. That's how charge works. 1 electron is the smallest charge you can get, and every amount of charge that we measure is some integer multiple of that. Okay? Also, next, a guy named Millikan does something called the oil drop experiment, and though I didn't have a place for you to write this down, over on the side where we talk about the actual amount of charge, okay, you might want to make a note that says Millikan's oil drop experiment, just so you remember where that came from. Okay? Millikan does an experiment where he actually determines the amount of charge that a single proton and a single electron have. And that amount is 1.6 times 10 to the minus 19th coulombs. That's what the capital C stands for, right? And I think we got that number on Wednesday as well, right? We got that out of the text? Yes? And a proton and an electron have exactly the same amount of charge, but one is a positive value and one is a negative value. Good there. All right, next. Charge is conserved. Conservation, another idea that we introduced earlier this year, right? What is the idea of conservation? When we say that something's conserved, what does that mean?
It's saved or it stays the same.
It's saved or it stays the same. Charge is going to be conserved because what does charge come from, or what does charge depend on? Subatomic particles. What are subatomic particles, Joe?
They are parts of the atom.
They're parts of an atom. Are they mass?
Yeah.
Yes. Can we get rid of them? Can we just destroy protons and electrons? No, right?
Wait.
Don't not it. It's made out of something.
But didn't you say that Dalton's thing was wrong when you said that they were indestructible?
Dalton said that atoms were indestructible. We can break an atom up into smaller parts, right? And we break those up into protons and electrons and neutrons. And actually we find out that protons, electrons, and neutrons can actually be broken down into smaller things as well, right? But there is something that, or at least we believe there is something that we can't destroy. But for this part here, because charge depends on electrons, and electrons are mass, we can't really destroy those electrons, therefore charge has to be conserved as well. That's going to be an important idea when we come across things a little bit later on. Good there? Total amount of charge is the same at the beginning as it was at the end. You'll find that there are some things that I throw up on the screen that you don't actually have to fill in your outline. All right, good there? How do we get an object to have a charge? What has to happen in order for, let's say, not that, but let's say this metal spring, if we want to give this a charge, what do we have to do?
To imbalance protons and electrons.
Things become charged, objects become charged when there is an imbalance of subatomic particles, mainly protons and electrons, right? We really don't care if the neutrons are different because they don't really, affect the charge anyway, right? But an object will become charged when it has an imbalance of protons and electrons. Another thing we find that when these protons and electrons become imbalanced, right? So, sorry. We'll get that later. When these protons and electrons become unbalanced, they start affecting other objects, right? For instance, zoom in here real quick. By the way, if you watch the video, you won't see the zooming in part because that only happens up here on the board. It doesn't happen on the computer screen. So, anyway, here. We take this plastic rod and we give it a negative charge and we bring it close to this negatively charged ball, and what do we know is going to happen there?
It's going to move away.
It's going to move away. Where'd you guys see that on Wednesday? Some of you were
Like over there.
on that little ball that was hanging from the string, right? Some of you were kind of playing tennis with it, even though you weren't actually touching it, right? Kind of like move it like this, move it like this, move it like this, okay? Same charges will repel each other, right? Okay? But on the other hand, okay, if we bring something that has a positive charge close to that negatively charged ball, what do we see happen? They attract each other. You saw that happen a couple of times on Wednesday as well. Where did you see this happen on Wednesday? There was one really obvious one.
Water.
The water, right? When you brought the rod close to the water, what did you see happen to the water stream? What happened to the little stream of water? It curved towards your rod, right? Because they're being attracted to one another because they have that opposite charge, right? That good? Chocolate.
Like what we were doing over there, the little things on strings.
Yep.
Could you do that on a bigger scale?
Yeah, you just have to have more charge, okay? We'll see if we get to there today. The other graphic organizer that you were supposed to do for homework talked about electric force, and we're going to get into that. That's like how much are we actually going to move it. But could we? Yeah, we could. It just matter how big of a charge do we have. Okay? But to finish this out right, like charges repel each other, opposite charges attract each other. Which most of you probably could have filled out before we did that whole thing, but whatever. pictures that you've seen before, but you don't have to pull out your notes from the other day. Just we'll look at it up here. All right. Bohr models of sodium and chlorine. So we take a look, right? We see sodium. It's got 2 electrons in its first ring, 8 electrons in its second ring, and then 1 electron in its outside ring, right? Therefore, we said it has 1 valence electron. What did we say sodium was looking to do with that 1 valence electron? Yeah. What did we say that sodium was looking to do with that 1 valence electron? Emma? Lose it, right? Then chlorine, right? 2 valence electrons, or sorry, 2 electrons in its first ring, 8 electrons in its second ring, 7 electrons in its third ring, right? 7 valence electrons. What did we say that chlorine was looking to do? Gain 1, right? So we said, what does that mean about these 2 elements as far as from a properties standpoint? Right? They're really reactive, especially with each other, right? We saw that one video with the big flash of light, blah, blah, blah. Okay? However, let's say that there isn't a chlorine atom around, right? That there's this sodium atom, but then, that's this. There's this sodium atom, but the next thing around it is another sodium. What's this sodium atom looking to do with that valence electron? Lose it. What's this sodium atom looking to do with its valence electron? Lose it. Is this one going to give its electron here? No. Right? This one doesn't want it. Okay? What happens if there's another one around? Are these electrons going to go from one atom to the next? No. But what they can do is that they can move from this, like if we take, let's say, this circle, alright, not that circle, well, could be that circle. That's pretty, this is not really going to be worth it when I'm done, but that's okay. Okay, let's say that. Alright, there's the valence electron from this sodium atom. This sodium atom is looking to get rid of that valence electron, so it passes it over here. But does that sodium atom want it? No. So then this sodium atom passes it on to here, but does this sodium atom want it? No. So what's now happening to this electron?
They're becoming positively charged.
Not exactly, because the electron can't be positively charged. But what we see is happening here with this one specific electron. What's happening to it? It's moving, right? Just goes from one atom to the next atom to the next atom to the next atom, because none of them want it, right? It's like a game of hot potato. Just pass it along, pass it along. It is kind of sad in that way, but, right? But luckily for you, that leads us to something that we call, where is it? A conductor, right? Conductors allow electric charges, especially electrons, to move freely within a framework of protons. This picture over here on the side represents those sodium atoms that I just put up on the board. Each one of them is a nucleus and a full valence shell, those big dots. The little dots represent those valence electrons. Do any one of these specific atoms want those valence electrons? Are any of them looking to pick up more electrons? No. So these electrons are just kind of out there. But that means that they can move easily from over here to over here to over here. Which means now we can have charges moving through a substance that has a bunch of unwanted valence electrons. What kind of elements have unwanted valence electrons? Alkali metals is a specific example of what? Alkali metals have an unwanted valence electron. Alkali earth metals have 2 unwanted valence electrons, right? All the rest of your metals are all going to have unwanted valence electrons. That makes them all generally what? That makes them all generally conductors, because they're all looking to lose valence electrons. So it allows the electrons to move easily from one to the next, to the next, to the next. Okay? Does that make sense? Something else that allows it to happen. It says when any part of the conductor gains an excess charge, that charge is distributed throughout the entire object. What does that mean? I'll draw you a picture and show you. Okay, good with this so far? I think you didn't even have to write anything down for that, did you? Awesome. Okay. So, on Wednesday, you saw the electroscope, yes? The electroscope, in case you don't remember, is that object that had the metal sphere up on the top, and then it had the metal rod that went down inside between the two glass things, right? And then on the end, there was these two little aluminum foil pieces, yes? Okay. The end result of the electroscope was what happened when you touched the little metal plate to the top of the electroscope. What happened to those two little aluminum foil wings? They separated out, right? So here's what happened. Up at the top of the electroscope, you added a bunch of electrons. There's a reason why I'm doing this, I promise. You added a bunch of electrons up to the top of that electroscope. But what was this part of the electroscope made out of? Metal, right? Do these extra electrons all like being next to each other up at the top of that electroscope? They all do what to each other? They all repel each other. So they're trying to do what? Get as far away from each other as they can. Conductors allow those charges to flow nicely throughout the whole thing, passing them along one atom to the next, one atom to the next, one atom to the next, one atom to the next. That means they start filtering through the whole electroscope and end up like this. Does that make sense? Okay, because they're trying to get away from each other as much as possible. But now if you look at these two aluminum foil leaves down at the bottom, what do you see about them? They both have negative charges. So what do they do to each other? They repel each other. And Joe, then what do you see then in the electroscope? Sound effect is what I was looking for. Too bad we won't be able to see that on the video, because that would have been worth watching. So. But anyway, does that make sense about how excess charge gets distributed throughout the entire thing? If one part of the electroscope gains extra electrons, they won't stay there. They'll spread themselves out throughout the entire electroscope or the entire conductor. Good? On the other hand, right, we have insulators. Okay. Insulators do not allow electrons to travel freely between atoms. First, let's go real, intuitively. If metals make good conductors, what kind of things are going to make good insulators? Non-metals, right? Just because they're opposite of metals. Okay? But if we look at their properties, right? Here's chlorine. Chlorine, 7 valence electrons. What did we say chlorine's looking to do in order to get itself stable? Gain 1. If an extra electron comes along, whether it's from sodium or wherever, is chlorine going to pass that extra electron along to the next one? Like sodium atoms do? No, right? Chlorine wants to hold on to those electrons. It doesn't allow electrons to flow easily from one to the next to the next. It's therefore not good conductors. Does that make sense? Okay? So, right? Like we just saw, non-metals are going to be your insulators generally, okay? But certain parts of an insulator may acquire other electrons, like we just saw in the electroscope, but it won't pass them through the whole insulator. Okay? But that doesn't mean that those extra electrons won't try to hold on to something. An example of an insulator that you saw holding on to charge on Wednesday was what?
The rubber tube.
The rubber tube, especially in which instance?
When it's tracking paper.
Right, when it tracks the paper. Right, Gabe, if we did it real nice and slow, what could you see happening as you pulled that rubber tube off of the tray?
The paper was sticking to it.
Paper was sticking to it, and then what was happening next?
The paper was sticking to paper.
Paper was sticking to paper, right? You were getting kind of like a little chain. None of those things are conductors, but they are showing behavior of having extra charge because they're attracting one another. So we can get a certain spot of an insulator to be charged, but it won't go out through the whole insulator. Okay? Good there? Okay. Next. Let's talk about charging. In order to get an object to be charged, what do we have to do? What's the end result have to be? In order for something to gain a charge, what does the end result have to be? How about if we just go, yes, it's either gain electrons or lose electrons. And that means now, Joe, what does it end up with?
Positive or negative.
Depending on whether it gained or lost electrons. But there has to be an imbalance of protons and electrons, not neutrons. Don't write neutrons down. Okay. Apparently I was typing too fast. Okay. Charging. Interaction between objects will result in an imbalance of protons and electrons. Imbalance of protons and electrons. Now, Joe, you said it properly, right? What's going to happen in order to result in this imbalance? Something is either going to what? What are the two things you said?
I said it's going to lose electrons.
Lose electrons or gain? No,
Electrons.
gain electrons, okay? Electrons are the things that move around, okay? Objects that gain electrons will end up with a negative charge. In order for an object to end up with a positive charge, it doesn't gain protons. It loses electrons. Okay. Electrons are the ones that are moving around. Protons don't move between one atom and one atom. Okay? Electrons can jump back and forth, but protons won't. So you either gain electrons or you lose electrons. Good there? Couple of ways that we talked about doing this, right? Oh, sorry. Direction of transfer depends on the material. Okay? So, first, charging by friction. We talked about this in our guided reading practice the other day, right? Charging by friction involves what? Rubbing, right? Involves, I mean, you know, if you want to have a dirty mind, I suppose. You know. I hear those things. Just so you know. Yeah, you know what you said, and I know what you said. Anyway, it is kind of a creepy picture, okay? But, so, in this case here, right? Balloon, you're rubbing the balloon on the hair, right? I don't get to do this one too often, but in this case, balloon and hair have a different attraction for those electrons. As we rub them across one another, what we'll see is that these electrons jump from the hair to the balloon, and then this electron jumps from the hair to the balloon, and then this electron jumps from the hair to the balloon, and it's supposed to show up here. But now we end up with the balloon having more electrons than protons, but it also results in the hair having more protons than electrons, right? Talk about.
Do you think your hair could pop a balloon?
Not pop necessarily. I suppose my hair specifically?
Yeah.
No, because it's actually short, but it's not real pointy. I have actually really fine hair. Like if it was before I lost all of it, it's not like real like pokey. It's actually real soft. But so no, I don't think my hair could. So. Yeah, I mean, you know, you have to have somebody who has like real like kind of wiry hair. You know, I don't know if it'll happen or not, but you know, maybe that can be an experiment later on in the
His
year.
hair is actually really soft.
What?
His hair is actually really soft.
Who's Mingus?
Bingo.
Minga would have been my guess, actually. I mean, you know, I can't say that I've ever actually felt Minga's hair. So, and I would like to say that for the record on recording, I have never touched Minga's hair. So, anyway, I'll trust you on that part. So, but yeah, my hair is actually is real, like, it's real soft. So I just don't have much of it. So. Yeah, this video. This one is definitely not a go home and listen to it and fall asleep video. This is a grab a popcorn and watch this one game. This is like a Sunday matinee right here. So. But anyway, charging by friction. You basically did this all class period on Wednesday, right?
Oh, speaking of Sunday matinees, if anyone watching this wants to come to the play this weekend, it'd be awesome.
I mean, not as awesome as this video.
Advertising all over
So,
the place.
I mean, I know this is
Advertisements
seriously.
are the best.
I
Just start
should
charging people.
Just
charge.
like a $5.
It's like airtime. So we can throw in commercials in the middle of it. All right. You did this pretty much all day on Wednesday, right? Okay. Charging by friction. You're using the contact between the two surfaces. One object gains, one object loses. Did anybody in doing the station in the back, the pitfall, okay? Did anybody take the rod, rub it with the cloth, you bring the rod close to the ball and it pushed away, but if you brought the cloth close to it, did anybody see what happened there? It came closer, right? Joe, if one object is gaining electrons and one object is losing, how many does the one gain versus how many the one loses? If one object gains, let's say, 100 electrons, how much did the other one have to lose? 100 electrons, because of that whole charge being conserved thing, right? So by friction, one object is gaining electrons, one object is losing electrons, exactly the same amounts. Okay? Conduction, or contact, right? Charging by conduction means electrons are transferred by direct contact. When did you see this happen? On Wednesday. We saw charging by contact. In the thing in the corner, the electroscope, right? When you touch the electroscope, with the aluminum plate, right, you're passing those electrons through the aluminum plate into the electroscope by direct actual contact, okay? That's an important idea, but another important idea coming out of charging by contact is the idea of grounding, okay? When we ground something, we are passing electrons either to or from the earth. But why is that so important? Because, remember back 2 chapters ago, we did like conversions to find out how many atoms were in, 10 grams of carbon or whatever it is, okay? You are a lot more than 10 grams of carbon, right? A lot of your body is based on carbon, okay? You're a lot more than 10 grams of carbon. So, you can imagine how many atoms exist just within your body. And in each of those atoms, there are lots of protons and lots of electrons, okay? But you're a huge number of atoms, but how many atoms do you think the Earth is? I mean, a lot more than you, right? Yeah, 10 more than you. So. But the Earth can gain or lose electrons by the boatload, bazillions at a time. And it won't actually end up gaining a positive charge or a negative charge. Does it technically? Yeah, technically it does. But there's so many there that even if you gave the Earth 100 bazillion electrons, that doesn't make a big difference in its charge overall. Okay? So grounding something means that we're either giving electrons to the Earth or getting electrons from the Earth. We end up with a balanced charge, or that object ends up with a balanced charge, but the Earth really doesn't end up with a charge. Is that okay with that? Then the last one is called induction, or inducing a charge. First, induction can only occur in conductors, okay? In this way. Conductors allow charges to move within the conductor to get an imbalance. For example, so here's a picture of 2 metal spheres, and you have this picture right there, okay? Over on the left-hand side, we bring in this negatively charged rod. All of the negative charges in these spheres, do they like these extra negative charges over here on the side? They don't. So they all start sliding across because conductors can do that, right? They allow negative charges just to flow freely. But if you look at the A and B group together, because they're touching one another, right? How many plus signs are there? 1, 2, 3, 4, 5. How many minus signs are there? 1, 2, 3, 4, 5. Is there a charge on this object as a whole? No. It's got the exact same number of positives and negatives. But what do we start seeing about those charges within that object? Are they balanced within the object? Number-wise, yeah, but there's definitely more positive charges on one side, more negative charges on the other side. Okay? If we wanted to, charged objects repel like charges within the conductors. Conductors have that ability to transfer charge real easily. If we wanted to, we could then split them apart. Now are those two objects charged? Now they are, but before they were just separated within the object itself. Good there? You see this happen a lot here. In a rainstorm, there is a lot of movement of water through the atmosphere, and that's causing friction. And that friction causes these things to be charged within a cloud. That ends up then with but it also ends up with the ground sort of being a positive charge. It's losing some of this water as it goes up. That causes this imbalance within the cloud. Negative charges go to one side, positive charges go to the other side. Do these negative charges like being next to one another? They don't. So what do? They look for the fastest way to get to the ground, to get to all those positive charges that are there. Even though that lightning strike is full of negative charges and it ends up in the earth, does the earth gain a charge? That's the whole idea of grounding. It doesn't. Good there? If we look at the calendar, there are some questions from this unit, or from the end of section 1, that relate to some of the topics we talked about today. Not all of them, but there are some questions there to take a look at. Okay? We'll finish this outline up on Monday and then get into currents. Thanks, everybody.
This class was like so fast.
What?
This is an awesome recording.
So, have a good weekend.